to the last one of these courses. So what I would like to do today is to go back to the GUE, eigenvalue density, and try to perform an asymptotic analysis of these correlation functions using the technology we saw last time. So this is, and the limit is going to be perhaps the most important object in random matrix theory, which is this sine kernel, which describes the determinantal eigenvalue process of GUE. So let's go back to GUE, as I said. So the density, if you recall the eigenvalue density of GUE, I will not write it again, but it has this Vandermonde squared structure, and the one particle measure is the standard Gaussian. So this is the one particle measure. It's a probability measure. You recall we work in these variables x, which were the eigenvalues lambda multiplied by square root of n, and this ensures that there's no n in this measure mu. So this is our standard Gaussian measure. So mu, that was easy, and so what about what is qk? If you recall, so the moral of the whole algebraic discussion from last time was that in order to compute these k-point correlation functions, it's in fact very easy provided you can find these polynomials qk, which are orthonormal with respect to this measure mu. So, we have two polynomials, they are the same. And by convention, so pk was the monic version of the polynomial and qk was the orthonormal, the normalized version of the polynomial. And pk was monic. And so we need to do two things. We need to find the pk's, monic polynomials pk that are orthogonal, and then we need to determine the normalization factor ck. So let's start by finding these orthogonal polynomials. So these pk, they are, how do we find orthogonal polynomials? I think many of you have seen this. This is so orthogonal polynomials with respect to this standard Gaussian weight. These are well known. These are the Hermite polynomials, and if you've done quantum mechanics, right? You've done the harmonic oscillator, and that's where they come up. There are slightly different normalizations. Sometimes people have 1/4 or 1, and there are different ways of representing them. So I would like to just recall this theory, because we anyway need the construction to derive a variety of identities, which we'll use later on. So, and it's anyway not hard. So let me review how to find these Hermite polynomials. So what is a sufficient condition for these polynomials to be orthogonal? So I would like to have pk of x, so they are real polynomials, pl of x e to the minus x squared over 2 dx is equal to 0 for all L less than k. Okay, so I'm looking for pk. Okay, let's say you pick a k, and then I would like to determine pk from this condition. It has to be orthogonal to all different L's. Now, without loss of generality, I can assume L is less than k. And I have this condition. Now, since these polynomials, all PL's L strictly less than k, they span the space of polynomials of degree strictly less than k, I can replace this condition. I can just say it's the same thing as pk of x being orthogonal to all powers of L, where L is strictly less than k. Okay? So that's a condition, and how can I let me in fact give this guy a name. This is an important condition that we will use. Now, how do we determine pk such that it satisfies this condition? Well, one way to do that, so we just need a sufficient condition, is if this function here, if this were the, if this is the kth derivative of any function, then by integrating by parts, this vanishes, right? So if this thing is the kth derivative of anything, then this is satisfied, okay? Now, of course, I want this thing, this whatever I have here, I want it to be a polynomial times e to the minus x squared over 2, so I can't choose anything I want here. So I want this, in other words, of something, of anything. And yeah, so if I want this guy to be the kth derivative of something, which means that pk, so let me call this something, let me call it r. So that means, this is a little side calculation just to see where this comes from. So pk e to the minus x squared over 2, this I want to be equal to dx to the k of some r. So pk is e to the plus x squared over 2 dxk of some r. And this has to be a polynomial. Okay, so that means I have to have something such that if I differentiate it k times and I multiply it by that guy, I get a polynomial. So it's clear what I have to choose for my r. Of course, if I differentiate exponentials, I never touch the exponential itself. I generate polynomials in front of it, so this form will work. And that's exactly what I will define. So this is sort of guesswork. Of course, once you have these formulas, it's very easy to check. But this deduction that I made, I think, is also quite convincing, right? So now, so I know that this polynomial here, this is a polynomial, right? That's obvious. I know by this argument that it's going to be orthogonal to all powers of L strictly less than k, and I would like it to be monic. So what does monic mean? It means that the coefficient in front of the x to the k is 1. Does anyone see what coefficient I need here to satisfy this condition? That's right, minus 1 to the power k, right? Because if I want to obtain, so I start differentiating this guy. If I differentiate it once, I pull down a minus x, okay? And then I differentiate again, and then I can always differentiate either the polynomial in front or the exponential. If I want to get the coefficient in front of the highest power of x, I always have to differentiate the exponential. I never differentiate the polynomial, and I get k minus signs. Okay, so I need this guy to compensate, and so this is monic. So this is monic. It's monic, and this is called the kth Hermite polynomial. Okay, so now let's figure out the normalization. So I want to find the normalization factor ck such that, so ck is just going to be chosen such that qk is normalized. So I want 1 has to be equal to qk of x squared e to the minus x squared over 2. Okay, so this is my condition. Now, by definition, this is ck squared, and then the integral of pk of x squared Okay, so now I need to calculate this integral, so let's just plug in the definition. So this is equal to ck squared, and I will make, just before I do that, I will write this as follows. In fact, for the calculation, I write it as a product of two pk's. And again, this pk, if you recall, starts with x to the k, and then I have lower powers. And this is orthogonal to all the lower powers, which means I can drop the lower powers. In fact, this is precisely this condition here. So this is precisely equal to x to the k, pk of x e to the minus okay, because of this condition star. That's how they were constructed. So let's plug in now my definition of pk. So I have x to the k minus 1 to the k, and then so this Gaussian factor here is going to cancel precisely this one here, and I have dx to the k e to the minus okay, and now I can just do k times integration by parts. Everything is, these are all smooth bounded functions. This guy decays very fast at infinity. I don't get any boundary terms. I will just differentiate, I'll integrate by parts k times. Every time I integrate by parts, I get a minus sign, so these minus signs will be gone, and I will just end up differentiating this guy k times, which gives me a k factorial. So this is integration by parts, k times, and I get ck squared times k factorial. And what remains is this integral, so these are all gone, and just this Gaussian integral, which is normalized. So the conclusion is that ck is equal to 1 over square root of k factorial. Okay, so this is how I get my normalized Hermite polynomials, just by dividing this with the square root of k factorial. Okay, this is all right so far? So if you recall what we need to do to compute these correlation functions, we need to understand this kernel, which I called Kn. So we need to analyze this kernel Kn, which was by definition, you take the sum, and then you have qk of x and qk of y. And these are all real polynomials, so we don't worry about complex conjugates. So the whole problem is a very concrete problem of asymptotic analysis. Namely, what happens as n tends to infinity, what happens to this kernel? And this type of argument we are doing here has very much the flavor of what people these days call integrable probability. It's become a huge industry starting in random matrices, these ideas have expanded to interacting particle systems and these growth models, KPZ type growth models, if you've heard about them. And the philosophy is exactly always what we are doing here, is first you start with some algebraic formulas, which are usually highly non-trivial, coming from some orthogonal polynomials or representation theory. That's what we did last time. And then you get to relatively concrete problems of asymptotic analysis, where you have to understand the asymptotic behavior of such expressions. And this can be a hard problem, but it's always performed using similar ideas, namely Laplace methods or saddle point methods and so on. And that's exactly what we're going to do here as well. So we have to do an asymptotic analysis of this kernel for large n. In fact, it's not totally easy. So we will see how to do it today. We will make one simplifying assumption. So you will see. The general case can also be done. It will just take a bit more time. So one intuition Kn formally. Does anyone see formally what does Kn tend towards? So as n tends to infinity, Kn, you can think of it as the kernel of an operator. Say in some weak sense or something. What does this tend towards? You have a family of, this is an orthonormal basis of your Hilbert space. Yes, it converges, this Kn will converge in some weak sense towards the delta function, delta of x minus y. So Kn is the orthogonal projection onto the range of Q0, Qn minus 1. These form an orthonormal basis, so this orthogonal projection in some weak topology will converge to the identity whose kernel is the delta function. So this can be made into a theorem if you wish, can be made more precise. We will not use it, it's for the intuition. So this is basically exactly the same thing as the theory of Fourier series, except now we have a slightly different basis, but it doesn't really matter. But here we are going to be interested in much more detailed questions. So what we are after is a much more refined question than the weak convergence of this Kn. So we have to work more. Okay. So in order to do this asymptotic analysis, I will need some properties of these Hermite polynomials, which are, as always, they are easy to derive once you know what you are looking for. So, a few properties. The first one is what happens if you differentiate pk. It has a nice formula in terms of pk plus 1 and x times pk. So we have such a formula. The next formula is a very important formula, and it's a formula that is ubiquitous in the theory of orthogonal polynomials. You will see the proof of this second formula does not rely really on the special nature of the Gaussian measure. It's an argument that applies to any orthogonal polynomials. Of course, the precise coefficients you get depend on the measure, on the underlying measure. But the philosophy that you have such a three-term recursion, so if you multiply pk by x, you can express it as a linear combination of pk plus 1 and pk minus 1. This is a general fact about orthogonal polynomials with respect to any weight. And this is sort of a famous fact. So this is a three-term recursion three-term recursion. And finally, no, I will need another identity. We will need an identity for the second derivatives as well. Okay, so that's another identity for the second derivatives, which basically follows just by differentiating the first one and applying the second one. And finally, and this is another famous identity, it's an identity that allows you to compute these kinds of sums. So you see, it's not totally easy to take asymptotics of such a thing, because you have these QKs. We will introduce scalings, which means that these guys will also depend on n, and then you will have a sum of n such terms. So that's a slightly nasty expression, and there is a beautiful formula in the theory of orthogonal polynomials which goes by the name of Christopher Darboux formula, which allows you, essentially by a telescoping argument, you'll see in the proof, allows you to express this kernel Kn simply as the following quotient. Okay, so you take Pn of x and Pn minus 1 of y, and then you take minus the one where you swap x and y, and then you divide it by, essentially by x minus y. In fact, if you want to get the right normalization, you have to have a 1 over n minus 1 factorial. And so this, as I said, is a famous formula. Due to Christopher and Darboux. Okay, so these are the basic algebraic facts we will need about these Hermite polynomials. So let me prove these. So the proofs are not difficult. You just have to know, basically have to know what to look for. I think you could all do them. On the last one you may have to think a bit, but you basically have to look for telescoping sum. So the first one is really, there's not much to say. You just start from the very definition that I gave of pk, and you differentiate it. You will have to differentiate. You have two terms you can possibly differentiate, and that's how you get these two guys. So I think I will not say more about that. Just from the definition of pk, and just differentiate. Compute. I think this is something that, in fact, it's more instructive if you do it yourself than if I do it for you. Maybe you can even do it in your head, but you can just start from the definition of this pk. Okay, so let's do the second one. And the second one has the proof is the general argument for any orthogonal polynomial. So what we want to do is to express, we will start from this function, and we will express it in terms of this orthonormal basis qk. And we will compute that the coefficients of this function in terms of this orthonormal basis, they vanish for all in all basis directions except in the direction of qk plus 1 and qk minus 1, and we'll be able to compute these coefficients exactly. So it's just doing these, using these standard Hilbert space methods of computing the coefficients of a vector in terms of an orthonormal basis. So let's introduce a scalar product, which is the one given by the Gaussian weight. Okay, so this is a nice Euclidean inner product on the L2 space with respect to this Gaussian weight. And then I write, so I will write this function x times pk of x. So I view this as an element in this L2 Hilbert space, and I write it as a sum, as an infinite sum of this guy projected onto QL. And I would like to rewrite everything in terms of the p's, so I recall that Q was P times CL. So I have CL squared PL x times PK, and then I have PL of x. And this coefficient, if you recall CL squared, this is precisely 1 over L factorial. And so one first observation, the first observation is that by this property that we call star, if the difference between k and L is strictly more than 1, then this will have to vanish. Why is that? Imagine L is bigger than k plus 1. That means this polynomial here has degree strictly less than L, and therefore this is 0. So okay, so PL x PK this is equal to 0 if k minus L is strictly bigger than 1. Okay? And of course the argument is symmetric, right? This x is a self-adjoint operator. In this scalar product you can bring the x over here, and then you swap the roles of k and L. So that's why it's a symmetric condition. Strictly bigger than 1, yes. Okay, so in other words, we have already got basically this form. This form here, we just have to figure out the coefficients. So there are 3 coefficients we have to compute. When k is L, when k is L minus 1, and when k is L plus 1. So let's do them. So let's do the one when L is k minus 1. So this is equal to x pk minus 1 pk. Okay, I can bring the x over to the other side. And now I recall that this guy was monic. And that means you can change the subleading. So that means this guy here is equal to x to the k plus lower order terms. And by star, you can change the lower order terms as you wish, because any polynomial whose degree is strictly less than k is orthogonal to k. So you can add all sorts of linear combinations of orthogonal polynomials. In particular, by adding appropriate powers of x with exponents strictly less than k, you can have a pk here, and this we know was equal to k factorial. Okay, so we know that this coefficient is equal to k factorial. Let's do the one where L is k plus 1. Well, the calculation is exactly the same, right? If I replace k by k plus 1 in this expression, then it's the same expression, except I have to the same. It's exactly the same calculation. In fact, you can take this result, replace k with k plus 1, and you get that. Okay, so finally we have to check what happens if you take L equals to k, x pk. And let's write this out as an integral. So we have x times pk of x squared e to the minus x squared over 2 and this vanishes because the integrand is odd, right? So this is an even function, this is an even function, it's the square of some, it's this, let's see, so I would like to use the fact that this is an odd function. So if I replace x with minus x, maybe that was a bit fast. I mean, this certainly vanishes. These Hermite polynomials are. So this is something I should probably have said, and that they are either odd or even. I think I did not prove that. Although, if you go back to the original form, yes. So if you go back to the definition. Okay, so this is a remark, so I will say this is even, because so the claim is pk is always an even or an odd function, and therefore this whole thing is equal to 0. And why is pk always even or odd? If you recall, so my pk of x was minus 1 to the k, and then I had e to the x squared over 2, dx to the k, e to the minus x squared over 2. Okay, now if you send x to minus x, then all that you will, so therefore from this minus x, you will get minus 1 to the k pk of x. Okay, just by the chain rule for derivatives. Is this okay? So from this expression. So using this symmetry property of pk of x, I see that and therefore pk of x squared is always an even function. Is this all right? Okay, so that's this property 3, and now you see we're done, right? So we've proved property 2. Sorry, we've proved property 2, because now we prove that all of these coefficients vanish except 2 when L is k minus 1 and when L is k plus 1, and when L is k minus 1, I get precisely this. Let's see, when L is k plus 1, then I get precisely. These coefficients will have to come out, right? So if L is k minus 1, then I get a k factorial, and yes, and then I have 1 over k minus 1 factorial, so I get a k, and if L is k plus 1, like here, then I get exactly k plus 1 factorial over k plus 1 factorial. Okay, so I get this expression. So this is end of So 2 follows. All right, so now 3, as I said, is a direct consequence of 1 and 2. I mean, you can do the calculation if you wish. You just take this guy, differentiate it once, and you differentiate it once, then you will get the derivative of, you will get the second derivative of pk, and then you will also get something relating to the first derivative of pk plus 1. Apply this formula once more, where k is equal to k plus 1, and then apply this second formula. You just play around with them and you will arrive at this equation. So I will not do that. So 3. So this is immediate from 1 and 2. Okay, so what remains is the fourth property, which is this Christoffel-Darboux formula. And there the key observation is the following. So let's compute. So if you recall, I just erased it, unfortunately, but I should have erased this board. Never mind. So if you recall, the Christoffel-Darboux formula, on the right-hand side, we have this, in the denominator, we have an x minus y, and on the left-hand side, we have a sum of these qk's. So let me write the qk's, let me bring this x minus y to the left-hand side, and I will write qk of x times qk of y as pk of x times pk of y divided by k factorial. Okay, so what I want to do is I want to sum up these terms where k goes from 0 to n minus 1. And now I will just use the property, this 3-term recursion. And you see also that this Christoffel-Darboux formula will works in general for any orthogonal polynomials or variant of it, because it relies only on this 3-term recursion from the second property. So I will have, so let me get, I will write 4 terms. So in the second part I wrote, so I will put this x onto pk of x. And then I use the second property, which gave me a 3-term recursion for x times pk of x in terms of 2 terms. Okay, so I'll get 4 terms. First, the terms with x's. So x times pk of x was equal to pk plus 1 of x, and then of course I always have the pk of y. And then the second term was k times pk minus 1 of x, and again pk of y. Okay, so those are the terms I get from the x, and then I have the same terms with the y. So I get pk plus 1 y pk of x minus k pk minus 1 of y pk of x. Okay, so the observation was that if I multiply such a guy with the x, then I have this nice 3-term recursion which gets rid of the x. And now, if you stare at this formula, you will notice that this is nothing but the difference of 2 terms that I call capital X of k, where capital X, let's say k plus 1, is equal to So this is somehow the insight to recognize this as a telescoping sum. Okay, so once I've told you this, you can just check. You can just check that that's how it is, right? If you have x, and then you have, I mean, this is maybe you see it. I think you can maybe do it in your head. You just take this guy minus the corresponding one with the k minus 1, and you still have to pull out a denominator 1 over k factorial. That means when you consider this guy, you will have a k minus 1 factorial in the denominator. You have to make it a k, which gives you a factor k in the numerator, which is precisely these two terms. Okay, so you can write this up carefully, but it's kind of obvious. And then you are done by telescoping. Right, so we know that the thing, this guy, that we wanted to sum, with k going from 0 to n minus 1, is just given as the difference of these guys. So that means this is just equal to x, x0, xn minus x0, and that was precisely the Christopher-Darboux formula. Okay. Is this all right? So these were these algebraic properties as a preparation. And now let's go back to the actual problem we wanted to solve, which was computing these correlation functions using the technology we developed on Tuesday and 2 weeks ago. So we can summarize. Now we have, thanks to this Christopher-Darboux formula, we have a much nicer formula for this kernel Kn. It's no longer a sum. It's just the quotient of the following form. So from proposition 44, part 4, so the Christopher-Darboux formula, we get that this Kn of x and y so this was the sum, this was just a definition, and now thanks to this Christopher-Darboux formula we can write it as Qn of x Qn minus 1 of y minus Qn of y Qn minus 1 of x, and everything is divided by x minus y. Okay, so that's a much nicer form, right? It has a you don't have any sum anymore. It has one slightly annoying feature, which is not a big problem, but it's slightly annoying, is that it has this apparent singularity in the denominator. So when x is equal to y, we have to watch out a bit, but you know that this is a fake singularity. Of course, if you look at the numerator, and the numerator vanishes when x is equal to y, and the left-hand side is, of course, also completely regular, even when x is equal to y. Okay, so this is what we will have to analyze. So now we have a great formula. We have lots of, we know everything we need to know about these Hermite polynomials. Here they are. We have a very explicit formula for Kn. So in principle, we can now set up the problem and let n tend to infinity, do some asymptotic analysis, and get the answer out. And that's exactly what we will do. I think, however, now is a good time for a pause. So we'll have a pause and do this asymptotic analysis after the break. So the goal is the behavior of these correlation functions. Now, what are we doing? So let me draw a picture now. So recall the big picture. This was the eigenvalue density of the GUE. And we have rescaled our eigenvalues, so these were our eigenvalues here. And what we would like to do now is to analyze these correlation functions, but rescaled around a point. So we would like to zoom in. So here's our eigenvalue, here's our spectrum. Okay, here's our spectrum, and of course, as you let n tend to infinity, if you would like to understand the correlation functions between, let's say, between two locations near consecutive eigenvalues, you will not see anything at all if you just let n tend to infinity in this limit. So in this scaling. So what you want to do is you pick a small window, you zoom in. So this is a window around E. You zoom in such a way that the typical spacing is of order 1. So here the typical spacing is of order 1 over n. The typical spacing is of order 1. So you rescale your correlation functions and then you take the limit. Okay, so what we will do alternatively in the language of point processes, this was the eigenvalue process of my matrix. I will define a new point process, which is this one just obtained by an affine zooming. So I choose a value E and I zoom in and I scale things up in such a way that the typical spacing between consecutive eigenvalues is 1. I get a new point process. I define the correlation functions of this new point process and I take the limit as n tends to infinity. And the question is, does this point process converge to some limiting point process? And the answer is going to be yes, it converges to the sign kernel determinantal point process, and that's what we would like to prove. So, so on the scale of eigenvalue separation around some point E. So I will choose a point E in the bulk of the spectrum, which is fixed, and I will zoom in around that point. So so in other words, so recall, so the eigenvalue process is I think this is the scaling that I used. Let me just check. I probably want an n to the minus 1/2. Okay, this is my scaling, and so we will define a rescaled. So define a rescaled we'll define a rescaled process. It's relatively transparent in this language of point processes. So what do I do to every point? I pick a point here and I take lambda I minus E, lambda I minus E. And then I want to blow things up by a factor that will ensure that the typical spacing is of order 1. So what is the typical eigenvalue spacing here? The typical spacing, eigenvalue spacing here, if you recall our discussion from the semicircle law, the local law, it's 1 over the density, right? The spacing is the 1 over the density, and the density is n times rho of, should I use rho v? Yes, I use rho v, and rho of v so that's the density of the semicircle law. So once again, so the expected number of eigenvalues in a small interval of length I is equal to n times rho of e times the length of I, and therefore the spacing is given by that number. So I want to blow up things by the following quantity. So this is my new point process. And so you have to just be careful when you do this rescaling. And here, in fact, it's convenient, at least for me, it's easier to, when you do this rescaling, to go back to the k-point intensity measures. Did you have this terminology in the exercises, I think, for a point process? The k-point intensity measure. You saw the k-point correlation function. So so this is just if you have a point process. So recall. So if you have a point process, so we have C, we have a measure mu. So in fact, we don't even need a measure mu. We have a point process on C. Then the k-point intensity measure, which I think we called pi k, of a set A is equal to the expectation we can write it like this, the probability that x I1 x ik is in A. Okay, this was the notation. I think this was the same. You should remind me. Did this appear on the problem set or not? This is the measure whose density is the k-point correlation function. So then the k-point correlation function mu Okay, so this is a function. So up to now we were talking about these functions. We will also talk about these functions. However, now it's more convenient to pass to these correlation functions, which are in some sense the more fundamental objects, simply because when we do this rescaling, the measures mu will change. Right, so on this scale, on the scale of the x's, the canonical measure mu, with respect to which we do everything, is the Gaussian measure. That was mu. However, if you zoom in, then you're sort of flattening the Gaussian measure, and it just becomes the Lebesgue measure. So we will, in doing this process, the Gaussian measure will become a Lebesgue measure. And in order to do all of this carefully, it's better just to go back to the K-point intensity measures. Then you don't have to worry about any of these mu's. So, in other words, so the K-point, so this was a review. So the K-point intensity measure on the original scale, in the variables in coordinates x, which were given by n to the minus n to the n square root. So in fact, we will have coordinates on 3. Would you mind closing the door? Thanks. Someone is doing some construction. So we have three scales. So we will work with the eigenvalue scale lambda, which is the scale on which the semicircle law lives. We had the scale x, which was convenient for this calculation. And when we zoom in, we will have yet another scale, new coordinates. So this K-point intensity measure is and this is precisely the correlation function with respect to the Gaussian measure that we have computed up to now. And then we have, and then I just multiplied. So I'm looking for this guy. This was called rho k. And so I multiply it with the product measure of these mu's. So from that I get 2 pi to the minus k over 2. And then I have k squared over 2 dx1 dxk. Okay, so that's a nice measure on Rk. So now I will do this rescaling. So I will do what I explained here. So in principle, it's just a fine scaling of such a measure. So the calculation is totally trivial. You just have to make sure you don't make a mistake. So work with rescaled variables where alpha is going to be, so these are going to be my new variables. So if you want in this picture, I work with lambdas, and here I work with alphas. Okay. Now alpha is going to be rho of E times n times lambda minus E. Okay, and this is equal to rho E times n times n to the minus 1/2 x. Okay, so these are my new variables. Now, from now on, I mentioned I will do one simplifying assumption. This is where I would like to do it. It turns out not just the algebra, but above all, the asymptotic analysis I would like to do becomes easier if we perform all of this at the origin. So the answer we get is exactly the same. That's a universal feature, that the limit of this point process, if you rescale by this correct density, is exactly the same everywhere in the spectrum. Just the calculations are a bit easier, in fact considerably easier, if you restrict yourself to the origin. So that's what I would like to do. And in good Hollywood style, I think I will end this year's class on a cliffhanger, simply because of time, lack of time. I would like to do this properly, so what I will do is I will explain. I will start this asymptotic analysis now. I will let you ruminate over it during the break, and we will finish it just in the first week after in February, so the first week of the next semester. Okay, so from now on, set E is equal to 0 for simplicity. I will explain, so next year, next decade even, I think, I will explain how you should do the argument we're about to do if E is not equal to 0. It's not fundamentally different. The asymptotic analysis becomes slightly more complicated, and but the basic philosophy is the same. Okay, so in other words, now, if you do this rescaling, so now E is 0, right? We agreed E is 0. So here was our K point. I just erased it, but we had the K point intensity measure in terms of these coordinates x. And now we just do a homogeneous rescaling of everything by square root of n times rho of E. Okay? And of course, you should not forget the Jacobian. And rho of 0 is equal to 1 over pi. Okay, the density at the origin is 1 over pi. So the K point intensity measure in rescaled variables is, so it's the same function that we had before, except we have to plug in the rescaled variables. So, so now, if you, just to remind you, so what does this mean? In these rescaled variables, we write it like this. So alpha I is going to be equal to square root of n divided by pi times xi. Okay, that's what we get. And so we get the original guy that was in the arguments were the xi, so expressed in terms of the alpha i's. Okay, we have this guy. Then I have the same factor that we had before. Then I have my Gaussian weights. So I have a pi squared over 2n. Now I start getting these kinds of factors. I have alpha 1 plus alpha k squared. And then I have to, of course, remember the Jacobian going from the, so here I have in the K point intensity measure with respect to the x's that I just erased, I had a Lebesgue measure, right? I formulated everything in terms of the Lebesgue measure. So when I go from these coordinates to that one, I get this guy to the k. So I have a pi to the k times n minus k over 2, and then I have d alpha 1 up to d alpha k. Okay, so this is just a trivial change of variables. So this is the K point intensity measure in my rescaled variables, but this is the guy that now has a chance of having a limit. And let me call this rho hat K n alpha 1 alpha k d alpha 1 d alpha k. Okay, so this is, and this is the K point k-point correlation function of rescaled process with respect to the Lebesgue measure. So once you've zoomed in, you don't see any of the Gaussian structure at all. Right? Everything appears flat, and that's why the Lebesgue measure is the natural measure to consider. So we have to analyze the limit, just the pointwise limit of these functions. We will prove that these functions have a nice pointwise limit, which is precisely given by a determinant of the sine kernel. We know already that these functions are given by determinants. This was this algebraic general discussion from the previous section. We know they are given by a determinant, a determinantal process, and we also know the kernel, that is the rescaled kernel Kn. So this was this proposition 43 from last time. So by proposition 43, we have the rescaled correlation functions. And again, this is a complete triviality. You just have to make sure you do the rescaling correctly. So it's an affine, in fact, even just a homogeneous rescaling. You just multiply your arguments alpha with this factor pi over square root of n. So this is, we saw that these correlation functions are given by a determinant. Where k hat n is the kernel, which was the sum of these Hermite functions in the new variables. And I did this carefully on my own. I think it's also best, if you want to check all of these rescalings, it's best that you do it carefully on your own. Maybe you can even see it in just in your head. So we plug in, so this has the x's. I will tell you in a minute what these psi's are. So the psi's are basically the q's. In fact, they're exactly the q's, except that I also have to include the Gaussian density. Now I include the Gaussian density into these guys, because the quantity that I computed, the previous Kn, was for the point process with respect to the Gaussian free measure, and now I'm computing the correlation functions with respect to the Lebesgue measure. Okay, so I just have to include also the Gaussian weights into these things, but this is not a problem. So I have pi over square root of n alpha and pi over square root of n beta. So this guy is a Qn, so I keep the same variables x. So recall this pi over square root of n alpha is my variable x. So this function psi n of x is Qn of x up to this Gaussian weight. Okay, so this is what you do. Notice I took the square root of the Gaussian weight because it has to go into both the psi n and the psi n minus 1. Okay, so this is the claim. This is a trivial rescaling. I think it's not helpful if I go through all the details with you. I mean, you see where it comes from, and if you want to, you can check it and make sure that these factors of pi and so on, they come out right. But there's nothing to it. Okay, so this is now a very concrete problem. I think we probably also used, maybe I should also mention, we used this Christopher-Darboux formula, right? So this is proposition 44. Maybe add. And okay. And this now has the explicit form we want, so we believe and we will show that this function converges for every fixed k, converges pointwise, in fact even locally uniformly. It's a very nice function, and to that end it suffices to prove the convergence of this function of two variables. And so one little remark that I sort of hinted at before is this might look a bit nasty if alpha is equal to beta, but actually it's not a problem at all, and this thing a priori is not defined when alpha is equal to beta, but by continuity, of course, you can define it, and one way to do that is just to use L'Hopital's rule. So by continuity of k hat n, and this is a continuous function, if you just go back to the original definition of kn, it's obviously a continuous function. It's an analytic function even. So we have k hat n alpha alpha is equal to, you can, for example, take the derivative in alpha in the numerator and the denominator. And if you do that, I differentiate in alpha, I get a 1 over square root of n, which kills that guy, and then I get a factor pi. So putting everything together gives you a phi prime. I don't touch the betas. Actually, I think the pi is cancelled. The pi is cancelled by this guy, right? If I take the derivative upstairs and downstairs, yes, the pi is going to be cancelled. And I have pi square root of n alpha psi. So this was psi n minus 1. I should put in the right indices. Psi n. Okay, so this is just using the fact that we know this to be a continuous function. So when alpha is equal to, of course, alpha, and I set this equal to alpha, and there should be pi. I thought there should be pi, but then I thought again that there should not be pi. So what if I differentiate in alpha? I get a pi over square root of n. The square root of n kills that guy. I get a pi, which is killed by this pi. What do we think? Pi or no pi? I thought there was no pi. In my notes I had a pi, so when I worked these things out beforehand carefully, I got a pi, but now I think I don't have a pi. I think, does anyone disagree with the pi? I think there's no pi, right? Application over chain rule. Okay, but the pi is not so important. The point is that this guy has a very explicit form, and now we know very precisely what these guys are, right? I mean, we know exactly how to differentiate Hermite polynomials. This is going to be a linear combination of Hermite polynomials. So this is not going to be that important. Just to tell you that this thing is also very well defined in terms of Hermite polynomials when alpha is equal to beta. Okay. So now let me state the main theorem of this whole section, entire section 4, which is sort of the punchline and which sees the emergence of this famous sine kernel. So proposition #45. So once more to summarize, k hat of n is a nice continuous, for every n, it's a nice continuous function of two real variables, alpha and beta. And the claim is that this function of two real variables, as n tends to infinity, converges locally uniformly to a limiting function, which is called the sine kernel. So and of course, if this guy converges, since this is just given by the determinant of this guy, then all of these will converge locally uniformly for any k. Of course, for this expression to make sense, you need k bigger than or equal to 2. Otherwise, I mean, the one point correlation function is, of course, you can consider it, but it's just 1. So that's not so interesting. Or a constant. So rho n hat k converges to a quantity that I call rho hat k locally as n tends to infinity, locally uniformly where this rho hat k, alpha 1, alpha k, of course, is a determinant in exactly the same form. K hat alpha I, alpha j, k, and so it's a determinantal point process. So as a review, so any point process whose correlation functions are given as determinants of such a kernel is called determinantal. And if you take a limit of a determinantal point process, you will again get a determinantal point process, and you just have to figure out the kernel, this k hat of the limiting process, and this k hat. So it's translation invariant, and it's given by the sinc function. So it's the sinc function that you multiply by pi. And so it's a kernel of a determinantal point process, hence the word kernel, and sine because it's a function of the sine. So more accurately, it should be called the sinc process, but sinc is not such a well-established function, so it's called the sine process. Okay? Is the statement clear? So this is a very beautiful result, and this is the first, historically, the first really deep result about random matrices. It was this whole calculation and the asymptotic analysis that we are about to do was understood by more or less independently by Wigner, Godin, Dyson, and Mater in the 60s. Or different parts of the calculation were done by them, and it was a remarkable calculation. It's an exact calculation. You see, we can do it here, but to come up with this calculation was not totally obvious. Once you get to this point, if you know some analysis, it's not too hard to conclude, and that's what I would like to do. So I will start the proof. I would like to abbreviate this function here with the scaling. I would like to distribute this square root of n evenly onto both of these guys here, and call it f. And also I would like to include the scaling of the argument by square root of n. The following way. So I write Fn, so for any So in the proof, I try to be consistent with my choice of letters. So I had lambdas, which were the eigenvalues on the original scale, alphas and betas, which were eigenvalues on the microscopic scale, and x's, which were on this intermediate scale. Now you just use x for the alphas. So I will rename alphas x's. They have nothing to do with the x's I was using before. It's just a bit easier to work with x's. So this is equal to n to the 1/4 psi n of x divided by square root of n. So in practice, this little n is going to be always capital N or capital N minus 1, right? Those are the ones we need. Those are the ones we'll need here. So the big work is to prove the following. So for any L, so for any fixed, I should maybe say fixed L, L, that the following limit holds. I claim that this function f of n minus L, again you should think of L as being either 0 or 1, is going to converge to the function cosine x Now, I can't really say that this function converges to this function because this function doesn't have a limit, but I can say that their difference, so in some sense it does converge to that one. This guy may oscillate like crazy, but for large n they are the same. So, stated precisely, this thing is equal to 0, locally uniformly in X. And let me give this equation a name. This is going to be the main work. So you see it becomes a very elementary, in principle, an elementary exercise in analysis. Here's my function. What was my function psi? I think the function psi is gone. Oh no, here it is. This is my function psi. I have a Hermite polynomial. I do a rescaling of my argument, and then I claim that this thing behaves exactly like this cosine. Okay. So let me just make a remark. So that basically all of the work is going to be to prove this, and that's a very nice asymptotic analysis argument using Laplace's method. So if you haven't seen this kind of asymptotic analysis, it's a very instructive argument that we will do. I think it should take us maybe 1 hour or so in February. So I'll leave you wondering about it over the break. I would like to explain to you how to conclude the main argument. How to conclude the main argument. So the claim of the proposition. So we still have to, there's some work to be done to deduce the proposition. So if you recall, the k hat n is just a quotient involving these guys. So let's compare it to the corresponding quotient involving these cosines. And there were these denominators to worry about. So let's first do it just for distinct values alpha 1 up to alpha k. Alpha 1, alpha k. By using the identity so you have the following identity, which is just a trigonometric identity that you can check. So cosine, I take exactly the expression for k hat that I had, and anytime I see an f, I replace it by this corresponding cosine. And what I get is cosine pi alpha So here little n is equal to n, here little n is going to be equal to capital N minus 1. Okay, and then I get the same thing where the roles of alpha and beta are reversed. And now you just look at, you take your favorite trigonometric identities and you recall in particular just the identity for sine of x plus y, right? You know the identity for sine of x plus y and you recognize this immediately as being the sine curve. Okay, so that's how the sine kernel arises. And in fact, if you've proved this, this will give a proof of proposition 45, assuming these arguments are all distinct. That's, I mean, basically, many people would be happy with that, but it's a bit of a pity because these denominators are really, that's the reason we have to assume they're distinct. The denominators are really fake. So let me just explain to you, in fact, this assumption that they are distinct is not important at all. And one way to do that is to write these differences as integrals of derivatives, which will kill the denominators, and then you can apply exactly the same convergence result. So this is a little parenthesis, if you really care about getting precisely the topology of convergence that I claimed also on the diagonals. So to prove so for all values of alpha, not just distinct, so we just write using the fundamental theorem of calculus. You write your kernel, instead of writing it as a quotient in terms of these k's, I can write it as an integral of derivatives in the following form. So this is equal to f n minus 1 pi beta. And this, I mean, this form is easy to check once you have it, just by using the fundamental theorem of calculus. Okay, so that's the derivative of f prime. You can check this just by applying the fundamental theorem of calculus. It's sort of a triviality. And now, so what did we gain? So you see, this is a very nice formula, because thanks to this integral representation, we got rid of the denominator. Okay, the price we have to pay is we have an integral of the derivatives, but we got rid of the denominator. And now, okay, we have to compute this derivative, but if you remember, f was basically just a Hermite function. And we have explicit formulas. We don't have good asymptotics for derivatives of Hermite functions. We have good asymptotics for Hermite functions themselves, but if you recall, this derivative can be expressed in terms of Hermite functions. So from proposition 44, this was part 1. Again, if you apply the chain rule correctly, the derivative of psi n, if you recall, f was just a rescaling of this psi n, and if you do this correctly, you should get the following expression. Okay, so that's what you get, and now we again see we get a nice linear combination of these Hermite functions. We can plug these in here, and you can. So this is a sketch. But you see now you've expressed, it's just a different expression. You've expressed k hat in terms of integrals of f's instead of a quotient of f's and something potentially singular in the denominator. And therefore everything is regular. You just have to use integrals, but this you can use dominated convergence and so on. So the argument is exactly the same. It's just slightly more complicated to write, which is why I stuck to this form here. But in this form, it's manifest that the diagonal, so when alpha is equal to beta, is not dangerous in any way whatsoever. So if you want to, so this was a sketch. I hope that having seen this sketch, it's clear to you that this is easy to do. It's sort of mechanical. If you want to, and I encourage you to do that, you can work out the details using this asymptotic estimate, which is non-trivial, but assuming that if you plug everything into these integral formulas, you can find the claim without any restrictions on alpha and beta. Okay, so this is what I wanted to do, and now all that remains. So what remains and that's going to be next year. Okay, so that's the last piece remaining. If you want to, you can even try doing it yourself. It's not totally obvious. You have to write things. If you've done some asymptotic analysis before, you might be able to do it. It's not terribly hard, but we will do it together carefully in the first lecture of next year. So the first lecture of next year will be the conclusion of this section, and then you will start. So Johannes Alt, who's been doing the exercises, will continue with this course, and he will move on to topics such as universality, which is going to be then the combining the two main things we saw in this semester. One was the local law for general Wigner matrices. The other one was this very precise calculation for a specific example of a sort of solvable Wigner matrix, the GUE. And then you can combine these two tools to prove that, in fact, everything we are doing here holds for general Wigner matrices, and that's called universality. And this involves a host of new techniques which rely all on the local law. So that's what Johannes is going to be doing with you next semester after I finish this. But for now, I'll stop here. Thank you.